So this is ELEN 451/557 MEMS and NEMS, as well as MSE 502 Microsystems Principle. And technically, it could also be called two other MSNT classes, but I don't think anybody enrolled in those. But it's all cross-listed for this one thing because I like to drive the registrar's office batshit insane. So I am Dr. Matthew Hartman with the Electrical Engineering Department. My office is upstairs in Nethkin Hall, room 211. My office hours for this quarter are Tuesday through Friday, 2 to 4:30 p.m., just as a heads up. Typically speaking, I will be in, I can't write on that, Nethkin Hall, room 120, which is literally like 3 doors that way, on Tuesdays and Thursdays from 3:30 to 4:30 to help with the circuits tutoring and all that kind of stuff. You're welcome to drop by because it's technically in my office hours. Just making you aware, I won't be physically here, or I won't be in my office at that time. Let's see. My email address is just my last name at latech.edu. And my office phone number is there, although I think at this point, like half of you guys probably have my personal cell phone number. Anyway, okay. So emergency class disruption policy stuff, in the event that classes get canceled due to an extreme weather event or another global pandemic or whatever, we'll move to Canvas and Zoom so we can be fully online. Some of you may have already noticed on our Canvas page that there is a Zoom link. I use that to record all of my lectures and all of that kind of good stuff. And then whenever the hell I get around to it, I post those lectures to my shitty YouTube channel. I will also put a link on our course page. So if you have to miss any class meetings or anything like that, there should be a recording that will allow you to catch up and all that kind of good stuff. I want to make it clear that I am in no way, shape, or form required to record my lectures or anything like that. So I post them whenever the hell I find the time to get around to doing it. I say that to politely say, leave me the hell alone. I'll do it when I can. Let's see. Course objectives, we're going to learn a whole bunch of stuff about MEMS because that's what this class is about. Textbooks and all that kind of good stuff. I really don't think they are required, but the official textbook for this course is Practical MEMS by Dr. Vili Kajakari. This book is out of print. This was my original PhD advisor forever ago. He literally wrote the book on this stuff and then left to go get a job in industry because tech doesn't pay for shit. Probably an actual better textbook is this Foundation of MEMS by Chang Liu. And I think this one is actually still in print. And then we have Microsystem Design by Steven Centuria. All of them are good books, and I use a combination of them to come up with my notes, as well as looking at research papers and all of that kind of good stuff. Because I record everything and I'll try to present you as much information as I can, it should not be necessary for any of you to actually waste money buying a textbook or anything like that. Let's see, disability disclosure stuff. If you need testing or classroom accommodations, please discuss them with me and sign up through the Office of Disability Services or Department of Testing and Disability Services. I can't remember what it's actually called right now, as soon as you can. Officially, our course attendance policy is what's found in University Policy 2206. Unofficially, you're adults. I'm going to get paid regardless of whether or not you choose to show up, so you do you. Like I said, everything is available. All the materials and stuff like that will be available online, so you can access them whenever you feel the need to. All that kind of good stuff. Academic honor code, that's boilerplate kind of stuff. In accordance with Louisiana Tech's Academic Honor Code, all students pledge, being a student of higher standards, they pledge to embody the principles of academic integrity. And then there's some more information here about academic misconduct, which is broken down into 2 sections, one on behavior and one on cheating. And I have to do this dumb thing. I don't know why. So for behavior, there's the official policy. Unofficially, don't be an asshole to each other or me. If you feel the need to beat me down in the parking lot, I'm a big dude, I don't know. Cheating, don't do it. Pisses me off. I have not had to do any honor code violations for cheating this academic year as of yet, but I have had to do it multiple times in the past. That is one of the few things that genuinely pisses me off. So we'll talk about assignments and all of that kind of stuff, particularly regarding, plagiarism and things like that, once I talk more about your projects and stuff for this course. Homework assignments, there will be approximately 8 for those of you that have had me in my undergraduate electrical engineering courses. You know that means anywhere from 4 to 17 based on just what I can get done. But I'll try to keep it to ballpark 1 a week regarding homework assignments for this class. The homework assignments are to be worked individually, but I'm not going to be pissed off or anything if you choose to work with your friends and all of that kind of good stuff to solve things. Just make sure that the work that you submit is your work. Let's see. Make sure that I can read things, or whoever the hell I find to grade this class can read things. If I can't read it or my grader can't read it, then I can just assume that you scribbled on the page and should get a 0. Let's see. There's going to be a project associated with this class, which will consist of a paper as well as a presentation. So how I want that to work, and I need to actually write this stuff down, which is why I have further detail on this assignment will be provided at a later date. But effectively, I'm going to expect the graduate students to be a one-person team where they have to write the paper and give the presentation as an individual, and undergraduate students will get to pair off in teams as that seems appropriate and all that kind of good stuff. That will be pretty much one of the 2 differences between the undergraduate version of the class and the graduate version of the class. The other difference will be in the exams. So there's going to be 2 exams given during the course, and for those of you that have had me in undergraduate electrical engineering classes before, I'm doing the same things the same way. Typically speaking, I give an in-class portion of a test and then also a take-home portion of the test where I can ask you more difficult problems that require the use of computer simulation tools, all that kind of good stuff. So that'll be the case for this class as well. So the workout problems and all of that kind of good stuff and maybe some simple theory questions will be fair game for the in-class portion of the test, and then more deeper theory questions and more difficult systems to analyze will be part of the take-home portion of the test. Your exam scores will be simply a combination of those 2 things. So each part will be out of 50 points, add those 2 together, and you have your 100 points for the test, total test score. Let's see. Don't use cell phones during the in-class portion of the test. Also, don't share calculators. I've had that happen before. Don't pass erasers back and forth that have shit written on them. I had that happen before. You guys are creative in your methods of just not doing the damn work. Anyway, the grading scale for this course is a traditional 10-point scale. As per usual, my official policy is there's no curving or rounding of grades offered in the class. So if you want to make an A, put in the work to make an A. For syllabus changes, I don't expect any changes to be made to the syllabus, but I reserve the right to do so. If I choose to do so, I need to let you know with ample time. More stuff about the emergency notification system, COVID-19 policy, which at this point is effectively just if you're sick, stay away from me or I'll be pissed off at you. Like I said, we use Zoom and all that kind of stuff. So if you need to miss class due to an illness, it's literally not a big deal. Just, follow along online and all that kind of good stuff. Counseling services are available for students that need it. These services are available for all Louisiana Tech University students at no cost to you. I know that in the winter quarter, and particularly around the holidays, can be difficult for some people. And I'm also aware that for reasons that are unclear to me and haven't been told to me, counseling services were utilized by students more last quarter than they have been in any previous quarter over the last several years. So apparently there's just something in the air that's causing mental health issues with Louisiana Tech students. So I'm just trying to make you aware of a place you can seek help for that. here's our tentative course schedule. So effectively today we covered the syllabus. I've got a little PowerPoint presentation where we're going to talk briefly about what MEMS are, and then we're going to get out of here probably a little bit early. On Friday, we're going to talk about microfabrication processes, and then going past that, we're going to get into the nitty-gritty of effectively circuits and statics smashed together at the micro scale and how to apply them to develop sensors, actuators, and all of that kind of good stuff. Let's see, we're going to focus particularly on a few classic MEMS devices in this class: accelerometers, pressure sensors, and gyroscopes. And then once we have our head wrapped around the principles, then we're going to get more into the research side of things and talk about MEMS utilization in different areas and kind of look at a current state of the art. Let's see, 2 tests are already listed on the syllabus. The last 3 days of the class are dedicated to handling your student presentations and all of that kind of good stuff. So that is the syllabus. Anybody have any questions or anything in particular? Okie dokie. Let me go to the correct thing. All right. So as I have mentioned, and hopefully you're all aware, this is MSE 502 and a couple of other things. I'm just going to have all of the slides that I use say that. So today we're going to talk a little bit about what MEMS are, the history of MEMS, and then their applications. So why is this not moving to the next slide? Son of a bitch. Okay, so what are MEMS? MEMS are micro electromechanical systems. So they are devices or systems that contain both electrical and mechanical components. And typically there is some conversion of electrical energy into mechanical energy or mechanical energy into electrical energy through electromechanical transduction. And that will take the form of a couple of different processes that we're going to look at. Probably one of the most common ones would be electrostatic transduction, meaning you're using capacitive attraction to either pull things together or force things apart by placing charges on them. Or the transverse of that would be you physically moving plates closer to each other or further apart so that the charge has to move on or off due to electrostatic repulsion, right? We'll also talk about piezo-resistive sensing. We can't really use that for actuation, but there are also going to be things like thermal actuation and sensing, piezoelectric actuation and sensing, all of those good kind of things, right? So it's always mechanical system and electrical system integrated together for a specific application. Many MEMS devices, in fact, the overwhelming majority of MEMS devices, or at least the classical ones, are simply scaled down versions of a microscopic design, or excuse me, a macroscopic design, right? So instead of having a huge, and I say huge, meaning it's on the order of a cubic foot sized accelerometer, using MEMS and modern CMOS manufacturing processes, we can actually make accelerometers and gyroscopes and things like that that have a footprint on the order of a square millimeter, okay? So a lot of these things are kind of like how I like to think about the dot-com boom and all that kind of stuff in the late 90s, because that's when I grew up. You have all of these billionaires like Elon Musk and stuff, whose brilliant idea to make his fortune, other than being born from a wealthy family, was what happens if banks were on the internet? Because that's all that PayPal really was. And now he's a jackass billionaire who's trying to control our government. But anyway, this is a similar thing. what happens if we try to take this device that has existed for 100 years and scale it down really small? And then what do you know? The first person that figures out how to do that is now another billionaire and gets a helicopter and a yacht and all that kind of crap. Okay. The development of microfab processes have led to a lot of new MEMS technologies and all of that kind of good stuff as well. Where are MEMS used? Literally everywhere. We have tens of them in our pockets right now, assuming your phone is in your pocket. If it's on the table, then you have tens of them in front of you. They're also in your laptops and all of that kind of good stuff. There are probably several MEMS devices in that projector and all of that kind of good stuff as well. They are ubiquitous at this point. Okay. Since the first MEMS devices were developed in the late 60s, they have pretty rapidly drifted from research-focused applications to consumer applications. Okay. So let's get into the history a little bit here. Okay. So the first MEMS device is the resonant gate transistor. Okay. The resonant gate transistor is a true MEMS device because it integrates a micromechanical structure, which is the cantilever gate electrode, into an electronic device. So let's kind of look at this thing here, right? So we have effectively a very long cantilever beam, excuse me, that is mounted through this anchor point to a substrate. This end, because of the cantilever beam, is allowed to be free. Now, I know this might be weird to think about now, but we'll get used to it pretty quickly. This long beam is effectively nothing more than a micromechanical spring. And it was designed in such a way to allow the spring to bend easily into and out of the plane of the electronics here. So effectively, we have an electrode over here on the right-hand side. And whenever, and we have an electrode effectively mounted on our beam as well. And whenever we apply a signal or a potential difference between this beam and this little electrode pad here, what's going to happen is that electrostatic attraction is going to occur. So like oppositely charged charges are going to try to move towards each other due to Coulombic forces. And that in turn is going to change the position of this gate electrode with respect to the surface of the wafer where the drain and the source were packed. So effectively, electrostatic actuation causes the threshold voltage of this particular device to change. So mechanical actuation influences the electrical behavior of this transistor-based device. And based simply on this schematic diagram, where we have a voltage source at the top, an output resistor, and then we are taking the output signal here at this node. This is a very simple common source amplifier there, where the output signal is modulated based on the input signal moving the threshold voltage around. Okay, so that's what's going on here. Hopefully you guys have enough electronics background to know basically how transistors work, but we'll talk about them in a little bit and all that kind of stuff too. Over here on the bottom, we have one of the first ever commercial MEMS devices. Let me see. Turn the light off so we can see it a little bit better. Hopefully you won't fall asleep, but it'll be okay if you do. So we have effectively the first iteration of inkjet printing here on the bottom right. Okay. So this device relies on what's called piezoelectric actuation. Anybody know anything about piezoelectricity? Electric rocks. Electric rocks, fair enough. So piezoelectricity, or the piezoelectric effect, which we're going to learn much more about in this class, is a property of some anisotropic materials, wherein if we apply a mechanical stress on them, meaning that we compress them or try to expand them, these particular materials generate an electrical signal or a voltage that is proportional to the amount of stress placed on that material. So effectively, and this is a two-way process, meaning that we can either mechanically deform the crystal and generate a voltage, or we can apply a voltage which will cause the crystal to mechanically deform. Okay, so we have both directions of the electromechanical transduction going on here. So effectively, what we have in this system is we have a piezoelectric crystal and then a very thin semiconductor membrane, okay, which gets used very significantly in pressure sensors and things like that. So if we apply a voltage across the terminals of this piezoelectric crystal, it is going to cause this crystal to place some amount of force, or put some amount of force on this thin mechanical membrane, which will in turn change the volume of the ink cavity and will force a drop of ink out. Okay? And then we apply a voltage of the opposite polarity, causing the crystal to shrink, and that creates vacuum pressure, which draws more ink into the cavity. And that happens over and over and over again. And that is literally how our inkjet printers work to this day. But this technology was developed actually way back in the 1970s. So inkjet printing is the oldest form of commercialized MEMS that exists. We've also got some microfluidics and all of that kind of fun stuff going on as well. So we've got a microfluidic channel here that effectively just emits ink outside of this little nozzle and all that kind of good stuff, but we'll talk about that kind of stuff later. Okay. So keeping on, in the 80s was when a lot of research, particularly due to an organization called DARPA, which is a US Department of Defense initiative, where they just funnel crazy amounts of money into doing interesting things that might have defense-related applications. But effectively, DARPA was pushing towards figuring out how to use MEMS devices to generate very small-scale electrical motors. So on the left-hand side here, we have an example of I'm going to use air quotes here, three-phase electric motor, because it does require 3 different voltage phases. But it's not three-phase AC like we would typically think of that is used in the power generation, distribution, and transmission fields. This is more of the 3-phase that we use to control a brushless DC motor, for those of you who have any idea of how brushless DC motors are controlled. Nathaniel, I'm sure you're in the process of figuring that out for EcoCar. Yes. But anyway, so effectively, this is another example of using capacitive actuation to do something interesting, right? So if we think of this portion of the stator here as one electrode, and this tooth of the rotor here as a separate electrode, effectively, because of how Coulombic forces work, if we allow this center wheel thing or this gear to rotate, it's going to try to rotate in the direction that will maximize the cross-sectional area of that capacitance. So like right now, if we activated terminal A or A prime, literally nothing would happen because the area between these two plates is already at its maximum. However, if we electrically excited this guy right here, Phi1, and this guy right here, Phi1 as well, because these two, so this portion of the stator and this portion of the rotor aren't fully aligned, what's going to happen is electrostatic forces will induce motion, and this guy will actually twist to make this area increase. And then we do it to number 2, and then number 3 in sequence over and over and over again, and we get rotation in a counterclockwise movement. Now, the gap between these two electrodes is on the order of a couple of microns. And this device was designed to rotate as freely as possible. Anybody care to venture a guess at what the actuation voltage is required to make this thing spin work? And this could spin at around 500 RPM.
Couple microvolts.
350 volts per phase. Takes well of a large voltage to induce movement there. We'll talk about why that is and all of that kind of good stuff. So you can probably infer from that why we don't use MEMS motors in all of our things like our electric toothbrushes and all of that kind of stuff. Instead, they're much larger, simple DC motors. And it's because it requires actually incredibly large voltages to induce the large amount of movement needed for these.
How big is this?
On the order of a few microns.
Surprised you could even get that to work without arguing.
Yeah. So, trying to think of what the dielectric.
Do they do it in a vacuum or something?
No, almost always this stuff is done in a vacuum for reasons dealing with air damping and all of that kind of stuff, which we're also going to talk about later. Because effectively at the micro scale, air is a viscous fluid. And so to eliminate drag on components and all of that kind of stuff, we either operate in a vacuum or have to effectively micromechanically pattern holes and all of that kind of stuff to eliminate squeeze film damping and all of that kind of jazz. So short answer is yes, it had to have been in a vacuum in order to do literally anything. And we'll talk more about why that is later on. Let's see. Now we get into the 90s and early 2000s, which is where we start to see a whole heck of a lot of MEMS in consumer applications. Okay. So this guy on the left is one of the first ever created accelerometers. This is a single axis accelerometer. I think this is an Analog Devices 80XL accelerometer. Let me look at my notes here. Yep. And so it utilizes capacitive sensing in order to determine an acceleration in a particular direction. This is an example of a very large capacitive cone drive. So effectively, and then once again, this is something that we're going to talk about in much greater detail whenever we get around to it. But effectively, we have interdigitated fingers or something like this. And as we either move the fingers in and out, the area of overlap for these parallel electrodes increases or decreases, thereby changing the capacitance, or we can move them up and down, also changing the amount of overlap between a couple of electrodes. So that would be how like a 2-axis accelerometer works, but this one was even dumber. This was a single axis because this is one of the very first ones. We could also do an accelerometer looking at this guy. So one of the things that I'm slightly confused about for this particular device, and it might be just because I'm looking at wrong, and these might all just be mechanical suspensions made of silicon beams, which are acting as springs. But you see all of these dots inside this center proof mass. That's typically done to reduce air damping, to allow a plate to move up and down or into and out of the surface established by the substrate freely without too much air resistance and all that kind of stuff. It might have just been done in this particular case to tune the mass of this, because it is at its heart a simple mechanical resonator. But anyway, this is already taking into account things like air resistance and all of that kind of good stuff. So these first 80XL accelerometers were developed for the automotive industry. So we didn't have airbags effectively until this was invented. And it's actually really interesting because if you go back and you look at the chips that Analog Devices, or the electrical integrated circuits that Analog Devices were creating for the automotive industry, they literally used to have all of the circuitry on one side and then this huge blank area, because they were still trying to figure out how to adapt their ability to make these devices into their CMOS processes. So they like had the footprint reserved, and it took them, I think, the better part of 8 years to figure out how to actually get everything to incorporate together into a bulk manufacturing process that could be repeated with a high yield. So they wasted tons of chip real estate because they knew once we figure this out, we're going to make tons of money, and they absolutely did. Over here on the right-hand side, we have a simplified example of Texas Instruments DMD, or digital micro mirror device, that is used still in a lot of movie projectors. I learned something about this device over the break when I was being a nerd and watching a documentary about Star Wars. So part of the reason that these devices literally existed was because George Lucas was harassing movie theaters and stuff like that about upgrading their projectors to be able to better show the images that he wanted to show for the Star Wars prequel series. And so he went to TI because he knew that they were involved with making the projectors, and was talking to them about what his needs were. And so the initial TI DMDs were literally designed to show Star Wars in the best resolution they possibly could. So that was pretty interesting. If you watch these documentaries, it's insane what the people that were working at ILM were involved with. Just as a tangent, because I'm a weirdo. You guys probably didn't know this, but for any of you who are guitarists or musicians, how many of you are aware of the Pig Nose brand of practice amplifiers? Anybody? Okay, well, they're a pretty damn popular brand of practice amplifiers used on recordings by the likes of Eric Clapton, Keith Richards, all of that kind of good stuff, invented by a guy that worked at ILM. How many of you are aware of Photoshop? Invented by a guy that worked at ILM. Not even kidding. So, Adam Savage was, and Grant Imahara also were associated with ILM. I don't think Jamie Heineman was. So, just more technology that we're still seeing in use to this very day. Let's see, what slide am I at? Go to my next slide, 6. Okay, so as the field of MEMS got larger and larger, research teams effectively led the development of MEMS into various application-specific subgenres, like optical MEMS, bio-MEMS, microfluidics, RF MEMS, and nano-electromechanical systems, or NEMS, etc. So, where we as consumers first really started seeing MEMS in our day-to-day lives was the use of accelerometers and gyroscopes and things like that in our personal devices. So here's a picture of an iPhone, I think 15, like the one that I have in my pocket. And this device has about 10 different MEMS. So not only does it have, instead of having a 3-axis accelerometer and a 3-axis gyroscope, it has what's called a 6-axis IMU, or inertial measurement unit, which combines both accelerometers and gyroscopes into a single package, and that's used to tell when you rotate your screen and all that kind of stuff. That's how it knows which direction is up. But there are also interesting MEMS devices like micro resonators and filters and all of that kind of stuff on the telecommunications side as well. So everyone's phone is literally chock full of MEMS. Then you have an Apple Watch, which has those same MEMS that are used for the telecom side of anything, because this is like a Dick Tracy watch and you can use it to communicate. But it also has MEMS in the touchscreen and all of that kind of stuff. And it also uses MEMS to be able to monitor biometrics and things like that. Then we have video game consoles. The controllers, once again, have those inertial measurement units where they use accelerometers and gyroscopes to tell what you're doing, tell how hard you're pressing down on the buttons, also providing haptic feedback and all of that kind of stuff. Most of that is accomplished by MEMS. The console itself, not just the controller, also contains MEMS. Then we have over here on the right-hand side, a simple router containing a lot of RF and optical MEMS to be able to route data efficiently and all that kind of good stuff. So we've talked a little bit about this already, so I won't talk about it too much, but most general purpose MEMS are used in a variety of applications. So we've talked a little bit about IMUs, accelerators, accelerometers, gyroscopes, magnetometers, just effectively measuring pitch, roll, yaw, and acceleration in directions. What you may not be aware of is that the touch screens on our phones and all of that kind of good stuff are also MEMS devices because they rely on capacitive actuation. Effectively, if you have two plates that are separated by some fixed distance, you know, hopefully that they exhibit some capacitance. Well, if you allow one of the plates to move freely, then that capacitance changes. And if you can locate where that changing capacitance is, that tells your processor somebody touched here. And that is how all of our touch screens work. Okay. Then we have things like optical MEMS, lots of lenses, diffraction gratings, all of that kind of good stuff. This right here is a MEMS Fresnel lens. Probably the most common place that we might see a Fresnel lens in use as a consumer would be in motion detectors. Okay. So if you have a motion detector that is based on passive infrared sensing, 100% it's using MEMS Fresnel lenses in order to focus the light. So effectively in that type of device, you have two different transistors, and whenever light shines on one of the transistors, it causes it to heat up and causes the output swing, the output voltage swing of that device to either go up or down. But when you have both of them illuminated at the same time, they cancel each other out. So effectively one voltage swings up, the other one swings down. When they're both illuminated, it cancels. These Fresnel lenses effectively allow us to direct light in a very, very tiny beam to make sure that only one of those transistor circuits is illuminated at a time so that we can see the direction that something's traveling. Then for ALI, we've got BioMEMS. So MEM devices for biological studies. So this is a ton of research goes into BioMEMS every year and has been for the last 20 years. That's a lot of how the biometrics and stuff in our watches and wearables work, but it's also the development of cameras, antennas, and all of that kind of good stuff for imaging. Also, I'm sure you've heard of, you know, system on a chip or lab on a chip and all of that kind of good stuff. Also MEMS. Microfluidics is a big part of BioMEMS as well. And then speaking of microfluidics, we have here a very dumb microfluidic device that some jackass who's currently teaching you developed as part of their PhD research. So for microfluidic devices, it's effectively just creating systems that can utilize very, very small amounts of fluids and direct them in creative ways to do interesting things like chemical sensing, DNA implication, and all of that kind of good stuff. All of that hubbub about PCR and all that kind of jazz that people were bitching about during the COVID pandemic is literally a direct MEMS application that I think most people just did not understand at all. Effectively, DNA amplification was simply you pass a sample through a microfluidic channel that has a temperature gradient across it. And as it goes through this serpentine microfluidic channel over and over again, every time it enters a hot zone, the DNA replicates, and every time it enters a cold zone, it stops. And that happens over and over and over again until your sample is amplified to a particular level. The number of channels it needs to go through increases the amplification, but it can't amplify something that isn't there. So all of the people talking about PCR testing always giving you positive results were completely wrong, because it couldn't happen if the COVID-19 virus didn't start at the inlet to begin with. It didn't exist in the device before. So anyway, just people not understanding the science were assholes and got in fights on the internet. Big surprise there. Then we have RF MEMS, so used for micro resonators, relays, capacitors, all of that kind of good stuff. This is a really, really interesting device over here on the right, because it is, remember much earlier I talked about how some MEMS devices were literally just scaled down versions of macroscopic devices. Well, this is an incredibly small scaled down version of a Russian tube varactor. Okay, so effectively, these old school Russian varactors or variable capacitors worked by one set of electrodes was fixed, and then the other set of electrodes was rotated in or out of phase, thereby changing the area of overlap between the plates and giving you a tunable capacitance range. Well, this research team figured out how to do that using torsional MEMS springs to be able to get a capacitive tuning ratio on the order of 34 to 1 or 3,400%, whereas most varactor diodes have a tuning range of about 11%. So this blew that out of the water. However, it's incredibly difficult and expensive to fabricate, so it never actually got used for anything. It's just a really neat application. All right, I think we're close to the end here. And then we have nano electromechanical systems. So these are even smaller accelerometers and all of that kind of good stuff, but they're also ushering in the latest versions of our modern electronics through the use of FinFETs, where effectively, instead of having simple planar transistors, we now have three-dimensional transistor structures to better dissipate heat, because the lower limit on how small we can make an integrated circuit is actually related to how fast we can get the heat out, so that we're not effectively just having all of that thermal noise overcome the signals that we're trying to process. And then the last couple of slides are just the references from where I got all those images and stuff. So anyway, consider yourself introduced to MEMS.